In this video, we're going to look at Unit 8, Lesson 8, which is on conditional probability. By the end of this lesson, you're going to be able to determine the probability of conditional events given a two-way table. To get started with this lesson, let's make sure that we understand what a 52 deck of cards looks like. And I'll put this back on most of the screens when you need it. But otherwise you can take a picture of it so you can look back at it. So you've got 52 cards in a deck, and 1/4 of them are hearts, 1/4 of them are diamonds, 1/4 of them are clubs, and 1/4 of them are spades. So there's the numbers ace, 2 through king. So ace through king in each of the suits. So there's 4 of each number: a heart, a diamond, a club, and a spade. And ace is generally considered a 1. And then you've got 2 through 10. And then you've got these face cards. So jack, queen, and king are considered face cards. If you're looking at an actual deck of cards, they each have a face on them. So they've got a person, a jack, a queen, and a king on them. So keep that in mind as we're looking at different probabilities. So on page 324 in your book, why don't you go ahead and answer the questions about this standard deck, then come back to the video. All right, so number 1, it says Noah will select one card at random from a standard deck. So he's going to select one card. What's the probability that the card that he selects is a queen? So let's isolate and figure out how many queens there are. So remember that there are 4 queens, 1 for every suit. So there are 4 cards considered winners in this case out of the total of 52. There's also, if you kind of isolate this and think about that these are kind of repeats, that each suit is a repeat, you've got 1 queen out of every 13 cards. And so this would also simplify to a 1 in 13 chance. And then a heart. So you can go ahead and certainly count all the hearts. So here's the cards that are considered winners for this one, all the hearts. There's 13 of those. You can also think of, so that's 13 out of the 52 cards. You can also think that hearts is one of 4 suits. And each of those suits is there the same number of times. So the heart is 1 out of every 4 cards. And then what's the probability that it is a queen and a heart, or a queen of hearts? So there's that 1 card in the entire deck that is a specific number and suit. So that's a 1 out of 52 chance. When Elena is choosing from only hearts, what's the probability that she gets a queen? So now she's not choosing from any of the other cards. We're knowing that she only has the hearts. So I think in this one in your book, it says that she picked out all the hearts and then she shuffled up just the hearts. Now what's the chance that she picks a queen knowing that she's only got 13 cards in her hands? So there's 1 queen out of those 13 cards. So conditional probability is defined as the probability of it happening under the condition that another event already occurs. So given something that already happens, or knowing that something has happened, in that first example, that would be number 2, where we already knew that Elena had isolated out only the hearts. So what's the probability she gets a queen under the condition she's looking at only hearts? So here's that situation for Elena. So the probability that the card is a queen under the condition, so this straight line here means under the condition. So when you see that in a probability, it's red under the condition, the card is a heart. So this is what we know has happened. So this is going to reduce our sample space. So we would read this, the probability that the card selected is a queen under the condition that the card is a heart. And what it means is the sample space is reduced to only the hearts. We're looking just at the hearts now. All right, so why don't you go ahead and try and use that new notation. So take a look at these two that ask you to write it with the symbols. So like this, but actually put the events in there. And then number 2 that asks you how you would say this symbolic notation. So try that, then come back to the video. All right, so in number 1, it says, what is the probability that a card is an 8? So let's write out the probability, and we're going to do the given or the conditional probability. So let's write this. And what is the probability that a card drawn is an 8? Give it under the condition that we know it's a spade. So we know we've reduced the sample space to just the spades. What's the probability that it's an 8? In this next one, it says, what's the probability that you roll a 6 under the condition that the number is even when we're talking a number cube? So what's the probability it's a 6 when we already know, or under the condition that we know the number is even? So if we think about a number cube, we've got the numbers 1, 2, 3, 4, 5, and 6. So we already know that whatever's been rolled is even. So we know it's a 2, a 4, or a 6. So we know it cannot be any of these. So then what's the probability that it's a 6? And then number 2, we actually want to write out how we would say this event. And so we would say, what is the probability? And this one should say that it's talking about rolling a number cube. So let's put that in there. So what is the probability when rolling a number cube that the number is even under the condition that it is greater than 3? So we already know that it's greater than 3. What's the probability that it's even? So similar to this last one, if we wanted to actually just think about this, we know that we've got the numbers 1, 2, 3, 4, 5, and 6. And if we know that our number is already greater than 3, so not equal to 3, so we know that it's greater than 3, then what's the chance that it's even? All right, so probability of A under the condition of B, so it's red, the probability that event A happens under the condition that B already occurred. And so Kieran is saying that that's similar to A and B happening. So the probability of A and B happening, which we've looked at from a table. Whoops. So in the warm-up, we looked at that it was a queen and a heart. So Kyron's saying what he's noticing is we could also do the probability that event A has happened under the condition that B happened times the probability of event B happening on its own. All right, so let's take a look at this rule that Kieran is using and see if it holds true on some of these. So the probability of a queen and a heart. So we can go and actually find how many queens and hearts there are, right? So here's hearts, here's queens. There is 1 queen of hearts. So we can just find that and probability from our sample space. So we know that the probability of a queen of hearts is 1 out of 52. So then if we take a look at this new notation, a queen given that a heart has happened. So now we know that we have selected a heart. So let me get this on here. So we know that a heart has already happened. So that's here. How many of those highlighted in orange are queens? And so then we see 1 out of the 13. And then what's the probability of a heart? Well, a heart is 1 out of the 4 suits, or 13 out of 52, which reduces to 1/4. So this is the probability of just a heart. this is the probability of a queen given that we know it's a heart. And if we multiply these out, so multiplying fractions, multiply tops times tops, so 1 times 1, bottoms times bottoms is 52. We see that we do get the same answer here. So whether you actually do it from your sample space or use this formula, we see that they're the same. Then in this second one, it says, again, the probability of a queen and a heart, which we already know is 1 out of 52. Okay, we looked at that. Now it's putting the condition that we know that it's a queen. So if we already know that we've drawn a queen, what's the probability that it's a heart? Well, that's a 1 in 4 chance. So we know there's 4 queens. One of them is a heart. And then what's the probability of a queen just in general in the deck is 4 out of 52. So if we multiply these together here, and I'm just going to write it as 1 times 4 on top and 4 times 52, because then these 4s I can just see will cancel and reduce to 1. So we're reduced to 1 out of 52. So these equal again. So what I want you to do is read page 324 in your book and see if it holds true on the 2 examples in your book, and then you can come back to the video. All right, so Kieran is looking at event A as the card is black. Okay, so the card is black, and B as the card is a king. Does the equation hold true? So we would look at the probability of it being black and a king. Then the probability that it's black under the condition that we've already chosen a king times the probability of a king. So let's take a look in our sample space and look at how many cards are black and a king at the same time. So we've got, all of these are the black cards. How many of those are kings? So that we can see kind of where these overlap. And so we see that they overlap 2 cards out of the 52. So we know that 2 out of 52 cards are going to be black kings. And then what is the probability that it is black given that we know under the condition a king has been chosen? So now if we know that a king has been chosen, how many of those are black? And so we see 2 out of 4 cards being black once we know it's a king. And then what is the probability in general that a king is drawn? And we know that a king is 4 cards out of the 52. And so if we multiply over here, again, if I just write it as 2 times 4 over 4 times 52, I'll see those 4s reduce out, and that'll simplify down to 2 over 52, which is the same as this side. And really it reduces to 1 over 26, but I just wanted to show that they were the same. All right, then number 2 says event A is a face card, B is a spade. So a face card and a spade. And face cards, remember, are jacks through kings. So we want it to be a face card and a spade. So we want these 2 overlapping. And so we see 3 cards out of 52 that are faces and black cards. Whoops. Then we want to take a look at how many face cards are there when we already know that it is a spade. Okay, so we already know it's a spade. So here's the spades. So how many of those spades, okay, there's 13 spades. How many of them are face cards? So the jack, queen, and king, that's 3. And then times the probability that it's a spade overall. So a spade, there are 13 spades out of 52. So then when we multiply these, we can see that our 13s are going to simplify out to 1. And this is going to reduce to 3 out of 52 and give us the same as just pulling the and off the table. All right, so let's look at conditional probability in a little bit of a different way when we know kind of how many objects are in a crayon box. So here they label out the colors of the crayons. And so there's 8 crayons in the box. 1 crayon is going to be taken out and removed. It's going to be set apart. And then we're going to draw a second crayon. So let's determine the probability that the first crayon drawn is a blue and the second crayon drawn is a blue. So for this, we can just take a look at what is the probability that the first is a blue. So there are 8 crayons in the box. 2 of them are blue. So that means we have a 2 in 8 chance of drawing a blue one the first time. Now we're going to multiply that by the probability of a blue the second time. So now we've drawn one of the blues already. So now we're down to just 1 blue and we're down to 7 crayons. So this, if we multiply it out, we get 2 on top, 56 on bottom, which reduces to 1 over 28. This would be the probability that both are blue. And we can see that it impacted the second probability because it reduced the sample space and the number of blue crayons. All right, in the next activity, we're going to be looking at 2 events of flipping a coin and rolling a number cube. And so I wanted to take a look at the sample space so that you'd be able to have the sample space written out so you could be looking at some different outcomes. So the option for flipping a coin is that we get a heads or a tails. And for rolling a number cube, we could get 1 through 6. So all of those options are going to be able to happen and together. So we could get a 1 and a heads, a 2 and a heads, and so on. So we're going to see 12 total outcomes possible. So go ahead and take a look at page 325 in your book and answer the questions about event A being that you get a heads and event B being that you roll a 4. Once you've answered those questions, come back to the video. All right, so are events A and B independent or dependent? And explain your reasoning. These are going to be independent because they don't impact each other. So one happening does not impact the other. You're going to flip a coin and then you're going to roll the die, and one event's probability does not impact the other. So let's go ahead and look at the probability of each of these different events happening. So what's the probability that event A happens? And A is that the coin lands on a heads. So we see heads in all of these options on the top. So that's 6 out of 12, or it happens half the time. So in exactly half of the chances, you get a heads. Event B is that the cube is a 4. So if we take a look at when is this going to be a 4, and we see a 4 here, 2 out of 12 times, or 1 out of 6 times, since it's 1 out of 6 options and it's going to repeat itself. So 1 out of 6, 1 out of every 6 times. What is the probability of the coin being a head given that we know that it's a 4? So under the condition that it's already a 4. So now we know it's a 4. So we know it's not any of these other ones. What is the probability that it's a heads given we know it's a 4? So this is going to be a 1 out of 2 probability. And then what would the probability be that it would be a 4 given that are under the condition that we already know that it's a heads? So now we know it's heads. What's the chance that it's also a 4? So that's going to be a 1 in 6 chance. Okay, so then looking at number 3, it says describe the meaning of each of these. So not B means that it's going to be not a 4. So this is going to be meaning we know it's a 1, 2, 3, 5, or 6. So what's the probability that we get a heads with one of those options? So we now know that it is not a 4. So we understand that this is out of play. What's the probability that it is a heads? Well, that's still 5 out of 10 times. So this is still a 1/2 probability. What's the probability that it's 4 given that it's not heads? And what does not heads mean? Not heads means tails. So now that we know that it's tails, so we're not looking at any of the heads, we know we're reduced to these 6 options. What's the probability that it's a 4? Well, still 1 out of 6. So are any of these probabilities the same? So is there a relationship between these situations? So there are probabilities that are the same. So the probability of A is the same as the probability of A when we know B has happened. And it's also the same as the probability when we know not B has happened. And then the probability of B is the same as the probability of B if A happens. And it's the same as the probability of if A does not happen. And that's because these are independent. So A happening has no bearing on B because the probability of A is 1/2. The probability when B happens is 1/2. And the probability when B does not happen is 1/2. Same with event A. So that's what this is showing you. If the probabilities are the same, then the events are independent. If you got different probabilities, then they would be dependent events because then their probabilities are being impacted by one another. So think of an example of 2 independent events. What is the probability of A given that you already know B has happened or under the condition that B has happened? And what is the probability of A? So maybe it goes back to drawing names out of a hat. So you have 10 names and you replace the name. So let's just do letters. So let's do A, B, C, D, E, that's 5, F, G, H, I, and J. So then what's the probability that we draw an A and probability of an F? So event A, well, we could just do A and B since we're doing events A and B. So what's the probability of A when we know B has already happened the first time? Well, the probability that we draw an A is 1 out of 10, okay, whether B has happened or not. So what happens in the first draw, we take B out, then put it back, still going to be 1 out of 10. What's the probability that we just draw an A on any given try? 1 out of 10. It's 1 letter out of the 10. If A and B are independent relationships, or independent events, what's the relationship between the probability of A when we know B has happened versus just the probability of A? And they should be equal when the events are independent. If the events are dependent, then these 2 probabilities will not equal each other because B happening impacted the probability of A. All right, for the lesson synthesis, let's look at a situation where we have these 6 students that have been selected to participate in a drawing to receive free movie tickets. 2 different students will receive free movie tickets. So that's the situation. Let's take a look at a couple of questions. So go ahead, pause the video, think about these questions, then come back. So why isn't it reasonable to roll a number cube twice to determine the winner, since there's 6 winners and there's 6 sides to a number cube? And this would be because you could roll doubles. So the same person would get the movie ticket, and we wanted different winners. So doubles would equal the same winner, and we wanted different winners. So what's a method that you could use to choose the 2 different names? So say just put the names in a bag on slips of paper, and then you can draw them. So using your method, are the events of picking Andre first and Elena second dependent or independent? And how could you find the probability of Claire being second under the condition that Elena was chosen first? So these are going to be dependent events because the probability of selecting either of them, if we looked at the probability of Andre, would be 1 out of 6. In general, the probability of Elena would also be 1 out of 6. However, we're drawing 2 names. So the probability of drawing Elena, given that you already drew Andre, so Elena's name is in there once still, but now we only have 5 names left because Andre's has been removed from the bag. So this probability is not the same here. So they're dependent. And then how would we find the probability that Claire is second under the condition that Elena was chosen? So remember that we've got, all 6 people on slips. And so let's say that this is Elena's. And so she was chosen first. So now what's the probability that we choose Claire? Okay, so the probability of Claire, given that Elena was chosen first, so Claire being chosen second is going to be a 1 in 5 chance. All right, so hopefully you can estimate probabilities, including conditional probabilities from a two-way table, knowing how to reduce the sample space and look at specific outcomes. You can check your understanding of this lesson by doing the lesson 8 practice problems, and if you need help, watching the video that goes along with that. And then you can also check your understanding by doing this cool down, and if you are struggling with the cool down, be sure to reach out to your teacher to ask for help.